Okay, let's look at another example of a net ionic equation. So here is some lead 2 nitrate, and it's reacting with sodium sulfate. So the question is, what do they form? And so underneath, we can go ahead and write the ions. So we've got sodium, we know is positive 1 because it's in group 1. And we've got sulfate, that's one of those polyatomic ions we should recognize. And then over here, we've got nitrate. And so the thing about nitrate, right, is it's got a -1 charge. But because there's two of them, we know that the total charge on nitrate must add up to 2 minus. And how does that help? Well, you see that lead has one of those variable charges because it's pretty low on the periodic table. It's one of those sort of heavy metal elements that we can't tell its charge from looking at its location. So we've got 2 nitrates that add up to -2. Then we know that lead must be +2. And so we are doing double replacement. So basically, we're just going to take each ion and play swapsies. So that lead is going to swap places. And instead of being pairing up with nitrate, it's going to pair up with sulfate. And we're also going to see the same thing for the sodium. So the sodium right now is paired up to sulfate. And it's going to go ahead and trade. And now it's going to pair up with the nitrate ion. And we can predict the formulas just like before. We just basically just play crisscross. So we take the 2 minus, becomes a 2. And the 2 plus becomes a 2, and the 2 minus becomes a 2. And this is one of those special cases where everything's 1 to 1. So if it's 1 to 1, right, we can just write PbSO4. So on the line above, we can replace that. And I don't know about green. So how about we write it in black? So PbSO4. And then again, the sodium nitrate, right? So that's a 1, and that's a 1. So that's pretty easy. So that's NaNO3. And we have to balance the equation. So we can immediately see we've got an issue because we got 2 nitrates here, and we've only got 1 here. And we also have 2 sodiums here, and we've only got 1 here. So we can kill 2 birds with 1 stone by putting that coefficient 2 right in front of the sodium nitrate. And things look much better for the other thing because if we go ahead and look at the lead, there's 1 lead, bingo, and there's 1 sulfate and 1 sulfate. So we're actually balanced already there. So our next thing we got to do is figure out the solubility. So, is one of those going to dissolve, or is one of those going to not dissolve and be a precipitate? So we can look at the solubility rules. Lead doesn't get mentioned on the solubility rules at all. It's nowhere on the list. But sulfate is all the way down at the bottom. And what does it say? So it says for sulfate, right, it is generally soluble. Let's straighten this up. And but the exceptions are if it has one of these 3 ions listed on the side: barium, which it doesn't; mercury, which it doesn't; but lead, it does. So because lead is one of those exceptions, then we aren't allowed to let it dissolve in water. So we get to write a big fat S next to it with a down arrow. And if we look at sodium nitrate on our solubility rules, it is pretty high up on the list, I think. So all sodiums are soluble with no exceptions. So the sodium nitrate gets to dissolve. And if we went on down, actually, we would see that all nitrates are soluble with no exceptions as well. So that looks pretty cool. So that is the full ionic equation, which is the first part of writing a net ionic equation. All right, so now we've got our molecular equation on the line above, and the net ionic equation, if you remember, anything that dissolves, we break down into its naked ions. And so the lead nitrate contains lead, 2, and it also contains the nitrate ion. And so in solution, they're basically just broken down. And if you look on the line above, right, so we've got a 2 down here, indicating that there's 2 nitrates for every 1 lead. But when they break apart, we actually replace those subscripts with coefficients, because in solution, the nitrate ions repel each other. Those negatives really hate each other, and so we put a 2 in front of them to indicate they're broken down into 2 things. Same with the sodium sulfate. So we've got 2 sodiums, and we've got 1 sulfate. So here we go. And that is the reactant side. And I'm going to go ahead, and because I did not plan very well, I'm going to write the arrow down below. And on the product side, so that lead sulfate, right? So the thing about lead sulfate is it's got that S next to it, which means it hasn't dissolved. So that means that we don't break it down. So in solution, those ions are stuck together. They are loved and committed and in a very stable marriage, and so they don't break down. but those sodium nitrates, right, those naughty sodium nitrates, they are dissolved. And so when they've dissolved, right, they've broken down and they formed 2 sodium ions and also 2 nitrate ions. And so that gives us our full ionic equation. So that's our full ionic equation. So I've gone ahead and rewritten it. Now if you notice that nitrate ion on the left and that nitrate ion on the right have not changed at all, and neither has that sodium there and there. So those are our spectator ions. And the thing about spectator ions, right, is they're just watching, they're not participating. So I can crash the nitrate and the sodium on the left with the nitrate and the sodium on the right. And that gives me the net ionic equation. So really what has changed? And so what has changed is a lead 2 ion that was dissolved in water and a sulfate ion that was happily dissolved in water have come together, and they have fallen in love, and they have stuck together so hard that they have formed a solid precipitate. And so that gives us our net ionic equation. Isn't that cool? And just to show you one more cool one, so I've kind of pre-written a couple here. So the molecular equation is lead 2 nitrate and potassium iodide. And it makes lead iodide plus potassium nitrate. And the net ionic equation, hopefully you can write by now. So you break it all apart to give the full ionic. And anything that's on both sides you cancel out. Those are the spectator ions. And you're left with lead and iodide coming together and making beautiful lead iodide solid. And if you're wondering, what does this actually look like? And in the left-hand side, I have a really cool video. So this is beautiful. When you did the lab where you looked at signs of chemical change, you actually did this reaction. So let's take a look and see. Oh, there's very cool music. It sounds like an Apple commercial. So there's some potassium iodide dripping down into the tube, and as it hits the lead nitrate in the tube, oh, isn't that gorgeous? And so that lead iodide is that beautiful yellow color, and it looks just like gold. In fact, some people call this the gold reaction. Nice. Oh, there's a third drop. Is it gonna fall? Plop. How beautiful is that? Oh no, 4 is just overkill. Wow, so those ions, essentially you got lead ions in the solution down here, and you've got iodide ions coming down for the drops that I think are done dropping, and then when they mix together they form that gorgeous lead iodide.